Hello, everyone. My name is Ahmed Shokry. I'm delighted to be here to present our work and efficient and practical black box verification of quantum metric learning algorithm. This paper is co-authored by Movahhed Sadeghi and Mahmut Kandemir from Penn State University. So quantum distance learning is an important topic in quantum machine learning because it is considered as a basic block in many quantum machine learning algorithms, such as quantum clustering algorithms and quantum classification algorithms. In quantum distance learning, we are trying to learn the optimal embedding between two groups. So here, for example, giving classical data, 2D classical data points, we need to train a unit tree U that accepts a point X and has some parameter theta, such that when we obtain the embedding or the encoding of uh, uh, of of each data point, we find that the angle between the two groups are separated according to a specific angle, such as here, for example, the angle between the two groups is pi over 2. So our problem definition is that giving a source of data points that belongs to one of two groups, red or green, and giving a verifier and the prover, our protocol used the verifier prover model where we have a weak quantum verifier. In other words, the verifier tries to the verifier can only measure. For example, it cannot actually apply any kind of unitary, and we have a prover that is full quantum and claim that it has a unitary U that accepts any data points and obtains the optimal encoding, and the angle between the two groups is separated with a specific angle theta, for example. And our goal here is that we need the verifier to be able to verify the angle separation between the two groups without having access to any details about the unitary or the axis that is used for embedding or anything like that from the prover side. So there are two main challenges here. The first challenge here is that uh, giving two states from two different groups to be able to estimate the angle theta, the verifier cannot directly measure the qubits because the measurement is destructive. Once the verifier tries to measure the state, the red state or the blue state, the state immediately will jump to one of two measurement devices. So for example, if the verifier tries to measure using the standard basis, the state will immediately jump to either 0 or 1, losing its state. So in turns, we will not be able to estimate the angle between the two groups, the red and the blue groups. The second challenge here is that the verifier does not know anything about the embedding process. So for example, assume that the prover separates the two groups with angle pi over 2, but uses Hadamard basis so that the two groups are separated with angle pi over 2. One of two groups is aligned with plus and the other group is aligned with minus. If the verifier tries to measure any state from any group using the standard basis, the verifier would not know whether the angle between the two states is 0 or pi over 2. This is because the Hadamard basis and the standard basis are two mutually unbiased bases. So the basic idea behind our approach is that giving an honest prover, then all the states or the fidelity between all the states that belong to the same group will be high, which means that we can consider them as only one state with many copies of this state. This, of course, will enable the verifier to reconstruct the state of each group, and in turns, the verifier would be able to estimate the angle between the two groups. Okay, so this is the basic idea behind our protocol. The verifier has access to a query that enables it to sample from classical data sample. So the verifier will sample 2n samples from the classical data, send them to the prover, and the prover will apply the unitary on them, and the prover will return the embedding of these 2n samples, and then the verifier will measure those embeddings, and hence the verifier would be able to estimate the angle between the two groups. Here, capital N is just a parameter, and in the experimental results section, we actually validate this parameter. Okay, so our protocol details, the protocol starts from the verifier side, and after obtaining, assume that we have only two groups, psi and phi, and we obtain the embedding for each state here from the first group psi and the second group phi. It is important here to note that once the verifier tries to send the classical data points to the prover, the verifier actually hides the class label or the group label from the prover, so that the prover does not know exactly whether the X or one of the 2n samples belongs to either the blue or the red group. Okay, so the verifier starts by measuring, by sampling n sample from each group, the psi and phi, send them to the prover. The prover will respond by the embedding or the encoding for each of the two n capital states, and then the verifier will measure those embeddings. The verifier actually measure the 2n capital states or embedding using one of the three measurement bases, such as the standard basis, the Hadamard basis, the circular basis, and the verifier will choose for each measurement device, choose between the three measurement bases at random. And then the verifier will be able to collect some summary statistics. So here, for example, the verifier will start by estimating the probability of obtaining 0 if it measures using the standard basis and the sample belongs to a psi group. Here, the verifier estimates the probability that the samples belongs to the phi group, and we obtain 0 using the measurement of the standard basis, the probability of obtaining psi and phi using the Hadamard basis measurement, and the probability of obtaining psi and phi using the plus I or minus I using the circular basis. And it is important to note that this kind of probability is really important because it will enable the verifier to estimate or reconstruct the state of each group. In a specific words, the verifier now be able, using this kind of summary statistics, is to estimate the density matrix of each group, psi and phi, and in turns, the verifier now can estimate the angle between the two groups by estimating first the fidelity between the two groups as the trace of a square root m, and then estimate the angle as cosine inverse of this kind of fidelity. Our protocol is complete and sound. Complete in sense that giving an honest prover that actually reports the correct angle between the two groups, the verifier now can accept this proof with high probability, 1 minus epsilon n, where epsilon n is a neglectable function in n. And our algorithm is also sound in sense that given a dishonest prover that claim an angle between the two groups that is not correct, the verifier will not actually accept this proof with higher probability. So here, for example, the probability that the verifier accepts this proof will be less than delta n, where delta n is neglectable in n. It's important that the idea behind this proof is coming from the fact that the prover does not know whether the data point X belongs to which group exactly. So for example, giving data X, which is general point, the prover does not know whether it belongs to the red group or the blue group. We validate our protocol using theoretical simulation results. So here, for example, in this figure, we show that for the different ground truth angle, our protocol can accurately estimate the angle between the two groups. We also validate our protocol using a practical model, QAOA penny lane embedding model, where we have a ground truth angle between the two groups that is something like pi/2. And if we increase the number of samples in our protocol in capital, we will eventually approaching or getting the true angle, and in turns, getting the true fidelity between the two groups. So since quantum metric learning is general than quantum classification algorithms and quantum clustering algorithms, our protocol can be easily adapted to verify quantum classification algorithms and quantum clustering algorithms. What's next? So we need to extend our approach to support more than two groups. Instead of having only a binary group, we might have 3 or 4 or more than two groups. And the second extension that we are working on is how can we extend our protocol to support a higher dimensional data points, something like 3-dimensional, 4-dimensional, 8-dimensional, and so on. Thank you.